which verifies that every geometric shape on every layer meets the foundry's minimum width, spacing, overlap, and countless other rules, often thousands of them. LVS, layout versus schematic, which mathematically compares the netlist extracted from the final layout against the original synthesized netlist to ensure they are functionally identical, proving you actually built what you intended.
Making sure no connections got accidentally broken or shorted during layout.
Exactly.
Yeah.
Also, antenna checks, which look for potential damage to transistor gates caused by charge accumulation during plasma etching steps in manufacturing. And sometimes electrical rule checks, ERC, looking for basic electrical problems like floating inputs or shorted power nets that LVS might not catch. 0 violations are required across the board here. Any error means the chip will likely have yield problems or functional failures.
Okay. Timing closed, physical verification clean. Are we finally ready?
Almost. The very last step is GDSI ASIC generation, which is the actual tape-out.
Creating that final blueprint file.
Yes. The verified physical layout database is converted into the standard GDSII format, or the newer OASIS format, which is the final data file that gets transmitted securely to the foundry. This file contains all the geometric patterns for all the masks needed to fabricate the chip.
And that is the point of no return.
That's it. Once that file is officially accepted by the foundry, the design phase is over. The immense effort shifts to manufacturing and then to post-silicon validation, getting those first physical chips back from the fab, putting them in a lab and testing them exhaustively to validate their real-world functionality against the original design intent. That's the ultimate moment of truth after maybe years of design effort.
It's an unbelievably complex, intricate process, but the results are these silent engines driving so much of our modern world. Let's talk a bit more about ASICs in the real world. Why do companies go through all this incredible trouble and expense to make a custom ASIC when there are often more flexible options like FPGAs available?
That's a great question. The simple answer is optimization. The huge investment, often millions, sometimes tens of millions of dollars in NRE costs for design tools, engineers, and mask sets, is only made for applications where the requirements are very well defined and the production volume is large enough to justify that upfront cost. ASICs are truly engines of optimization.
So they're chosen when performance or power efficiency or cost at scale are absolutely paramount, and you can't achieve those goals with off-the-shelf parts.
Exactly. And nowhere is that more evident today than in data centers and high-performance computing, especially with the absolute explosion in demand driven by artificial intelligence.
Right. AI workloads, particularly training large models, demand computational power that general-purpose CPUs just can't handle efficiently. Even GPUs aren't always the perfect fit, are they?
Correct. While GPUs are great for parallel processing, they are still general-purpose to some extent. The massive matrix multiplications and tensor operations at the heart of deep learning are so specific that you can get huge gains by designing hardware just for that. Google's Tensor Processing Unit, the TPU, is the quintessential example of an AI ASIC.
How is it different?
It's custom-built from the ground up, specifically for those matrix tensor operations. It strips away all the unnecessary logic found in a CPU or even a GPU, focusing hardware resources entirely on accelerating neural network computations. The result is orders of magnitude better performance per watt compared to using CPUs or GPUs for those specific tasks.
And that translates directly to cost savings in the data center.
Immense savings, especially in power consumption at scale. These TPUs now power huge parts of Google services: search, translate, photos, and of course, training and running their large language models. The whole market for AI acceleration, especially for high-volume inference, running trained models, is rapidly shifting toward these specialized ASICs because the PPA advantages are just too compelling.
Okay, data centers make sense. Another area where ASICs seem absolutely indispensable is consumer electronics, maybe most obviously inside our smartphones. You called the smartphone SOI a marvel of integration earlier.
It truly is. It's probably one of the most complex types of ASICs regularly manufactured in high volume. It represents the absolute pinnacle of PPA optimization, packing an incredible amount of functionality into a tiny battery-sipping package.
So chips like Apple's A series or M series or Google's Tensor chips in their Pixel phones, these aren't just CPUs, are they?
Not at all. They are heterogeneous systems, complex collections of numerous specialized ASIC blocks integrated onto a single die. You'll find multi-core CPUs, powerful GPUs, dedicated image signal processors, ISPs, for the cameras, specialized video and code engines, security enclaves for sensitive data, and crucially in modern chips, dedicated neural engines or NPUs. neural processing units.
So the neural engine is essentially an ASIC within an ASIC, designed specifically for running AI tasks efficiently on the device itself.
Exactly. It powers features like computational photography enhancement, real-time language translation, voice recognition like Siri or Google Assistant, and biometric authentication like Face ID. This kind of tight integration, low power consumption, and high performance for AI tasks would simply be impossible to achieve with separate discrete chips in a device constrained by battery life and size. It has to be an ASIC.
Right. The low power and high performance are just non-negotiable for a handheld device. What about cars? Automotive systems seem like another huge area for ASICs.
Absolutely. The automotive industry is undergoing this profound transformation toward electrification, connectivity, and autonomy, and ASICs are critical enablers for all of it. And these aren't just any ASICs. They have to meet exceptionally high reliability standards like AEC Q100 qualification, often functional safety requirements like ISO 26262, and operate flawlessly in very harsh temperature and vibration environments.
So we're talking about the brains behind advanced driver assistance systems, ADS, and eventually fully autonomous driving. Companies like Tesla, Mobileye, NVIDIA are building custom ASICs for this, right?
Yes. Processing the vast amounts of data coming from cameras, radar, LiDAR sensors in real time, making safety-critical decisions. This demands massive specialized compute power with very low latency and incredibly high reliability. Custom ASICs are really the only way to achieve that within the power and cost constraints of a vehicle.
And beyond ADAS.
ASICs are crucial elsewhere too. Powertrain controllers, vehicle dynamics control, sophisticated battery management systems, BMS, in electric vehicles that monitor hundreds of battery cells, power electronics for motor control and charging, and complex in-vehicle infotainment systems, managing multiple high-resolution displays, connectivity, and audio. Cars are becoming rolling data centers, and ASICs are powering much of that.
And one more area, networking and communications. High-speed data seems like a perfect fit for custom hardware.
Definitely. ASICs have long been at the heart of high-performance networking equipment. The core silicon inside massive carrier-grade switches and routers, capable of processing network traffic at terabits per second that's specialized ASIC territory. And similarly for 5G and a future wireless infrastructure, the complex digital signal processing needed in base stations to handle massive bandwidth, numerous antennas, MIMO, and achieve ultra-low latency relies heavily on custom ASICs and specialized processors. Essentially, anywhere you need the absolute best performance, power efficiency, or cost per unit at massive scale for a well-defined task, an ASIC is likely the answer.
This brings up a really important practical question for anyone developing an electronic product. When do you choose to go through the immense effort and cost of designing a custom ASIC versus using something more flexible, like an FPGA? This seems like a critical study in trade-offs.
It absolutely is. This is a fundamental engineering and business decision that product developers wrestle with constantly. It really boils down to balancing that ultimate optimization an ASIC offers against the on-the-fly flexibility and faster time to market of an FPGA.
Okay, so let's make the case for ASICs first. We've established they are the pinnacle of PPA and scale. Unmatched performance, lowest possible power consumption, smallest physical area because there's zero extraneous logic.
Right. Every transistor is there for a specific purpose, optimized for that one job.
And critically, at high production volumes, ASICs offer the lowest cost per unit. That upfront NRE is huge, but if you're making millions of chips,
that NRE gets amortized over all those units, making the cost of each individual chip potentially very low, maybe just a few dollars or even cents for simpler ones. This is why your smartphone, your TV, your Wi-Fi router, anything produced in millions almost certainly contains multiple ASICs.
But the downsides are significant. First, those prohibitive NRE costs, we keep mentioning millions, potentially tens or hundreds of millions, for the EDA tool licenses, the large engineering team salaries over years, and especially the mask sets required for manufacturing, which get incredibly expensive at advanced nodes.
Absolutely. And related to that is the long and complex development cycle. Designing, verifying, and taping out a complex ASIC can easily take 12 to 24 months, sometimes even longer.
And the biggest one, perhaps, complete inflexibility. Once that design is taped out and manufactured, it's literally frozen in silicon.
Exactly. If you find a bug later, or if market requirements change, you can't just issue a software patch. Your only option is a respin, fixing the design and going through the entire expensive mask and manufacturing process again. That's a costly mistake you want to avoid at all costs.
Okay, so that's the ASIC. Optimized, cheap at scale, but expensive upfront, slow to develop, and inflexible. Now what about the alternative? FPGAs, field programmable gate arrays.
Right. An FPGA is essentially a generic integrated circuit filled with an array of programmable logic blocks and programmable interconnects. You don't design the silicon itself. You buy an off-the-shelf FPGA chip and then configure or program its internal logic to implement your specific function.
So the big advantage is flexibility and reprogrammability.
Absolutely. That's the killer feature. You can program an FPGA, test it, find a bug, fix your configuration code, and reprogram it in minutes or hours. You can even update the functionality of FPGAs already deployed in the field via a remote update, just like software.
That's huge for bug fixes or adding new features after launch. What else?
Fast time to market. Because you're essentially doing software-like development, targeting existing hardware, the design cycle for an FPGA project is significantly shorter than for an ASIC, maybe weeks or months instead of years. You can get a working hardware prototype extremely quickly.
And the cost structure is different.
Completely different. There are essentially low to zero NRE costs. You buy the off-the-shelf FPGA chips. You don't pay for custom masks or foundry runs. This makes FPGAs ideal for prototyping, research and development, and for products with low to medium production volumes where the high NRE of an ASIC wouldn't be economical.
Okay, but there must be downsides. We know ASICs win on PPA, so FPGAs must have inferior PPA.
Yes, significantly so. That programmable logic fabric, all the configurable blocks and flexible wiring, adds substantial overhead compared to a dedicated ASIC layout. This means FPGAs are generally slower, much more power-hungry, sometimes 10x or more, and physically larger for the same functionality compared to an ASIC equivalent.
And the cost per chip.
The high per-unit cost. While the NRE is low, the cost of each individual FPGA chip, especially the large, high-performance ones, can be quite high tens, hundreds, sometimes even thousands of dollars per chip.
So you wouldn't put a $1,000 FPGA in every smartphone?
Definitely not. They're economically unviable for high-volume, cost-sensitive consumer applications where the ASIC's low per-unit cost dominates.
But there's a symbiotic relationship here, isn't there? FPGAs are often used in the ASIC design process itself.
Yes, very much so. Large FPGAs are frequently used as prototyping platforms for ASIC designs.
How does that work?
Design teams can take their actual ASIC RTL code, synthesize it to target a large FPGA board, and create a hardware prototype of their ASIC. This prototype might not run at the final ASIC speed, but it runs fast enough to validate the hardware functionality in a real system context. And crucially, it allows the software development teams to start writing and testing their drivers and applications months before the actual ASIC silicon comes back from the fab.
So it's a critical de-risking strategy, and it enables parallel hardware-software development, potentially saving huge amounts of time in the overall project schedule.
It absolutely is. Using FPGA prototypes to validate the ASIC design and get software running early is a very common and valuable technique in the industry. It bridges that gap nicely, letting you leverage FPGA flexibility before committing to inflexible ASIC silicon.
Okay, that comparison makes the trade-offs really clear. Now let's look ahead again. Let's gaze into the crystal ball, or maybe just the research papers. What are the future trends and research directions that are really shaping the future of ASIC design? I imagine it's still being driven by Moore's Law, but maybe in new ways, and also by these insatiable new demands from things like generative AI.
You're spot on. The relentless march of Moore's Law, or perhaps more accurately, the economic drive to pack more functionality into smaller spaces, continues to be a primary driver. We're seeing the ongoing migration to advanced process nodes, 7 nanometer, 5 nanometer, 3 nanometer, are in high volume now, and foundries are actively developing 2 nanometer and even nodes below that, sometimes called angstrom scale nodes.
And the benefits are still the same: higher density, faster transistors, lower power per transistor?
Fundamentally, yes. Each new node allows you to cram more transistors into the same area, which can mean more performance, more features, or lower power. Potentially all three, although the gains become harder to achieve with each generation.
But this progress comes at a steep cost, right? Both financially and in terms of sheer design complexity. The physics at that scale must be absolutely wild.
Immense complexity, yes. As transistors shrink to just tens of atoms across, quantum mechanical effects become significant. Physical effects like parasitic resistance and capacitance of the tiny wires, process variability from atomistic fluctuations, signal noise, and crosstalk. These all become dominant problems that engineers have to meticulously model and mitigate.
And the cost?
The cost of building a new fab and developing these leading-edge processes runs into the tens of billions of dollars. The manufacturing itself relies on incredibly precise and expensive techniques like extreme ultraviolet (EUV) lithography, using wavelengths of light almost in the X-ray spectrum. The mask sets alone for a single advanced ASIC design can cost millions of dollars.
So designing for manufacturability must be paramount.
Absolutely. Design for manufacturability, or DFM, becomes a critical, non-negotiable part of the design process. You're not just designing a circuit, you're designing a layout that can actually be reliably manufactured with acceptable yield using these incredibly complex processes. It requires close collaboration between designers and the foundry.
This escalating cost and complexity, especially for very large chips, must be driving new architectural paradigms. You mentioned chiplets and heterogeneous integration earlier. Is that becoming the main path forward?
It's certainly a major trend, seen as a key way to overcome the challenges of building enormous monolithic SoCs on the most advanced nodes. The concept is, instead of building one giant chip, you disaggregate the system into several smaller, specialized dies called chiplets.
And the advantages?
Each chiplet can be manufactured on the process node that is most appropriate and cost-effective for its specific function.
So you could have, say, the high-performance CPU cores on a cutting-edge 3-nanometer process because they really benefit from that speed and density.
Right. But maybe the analog I/O interfaces or certain memory controllers don't need that bleeding-edge performance and could be built more cheaply and with higher yield on a more mature, less expensive process node, like maybe 12 millimeter or 22 millimeter.
And then you integrate these different chiplets together into a single package.
Exactly. Using advanced packaging techniques, often called 2.5D or 3D integration, which allow very high bandwidth, low latency connections between the chiplets.
That sounds like a genius approach. What are the big benefits?
Several. Dramatically improved manufacturing yield, because smaller dies are much less likely to contain defects than one giant die. The ability to mix and match best-in-class technologies from different process nodes or even different vendors. And it facilitates IP reuse at a larger scale. You can potentially reuse a proven I/O chiplet across multiple product generations. It's seen as a key strategy for continuing system-level scaling in the post-Moore's Law era, or maybe the more than Moore era.
And are there standards emerging to make this easier to allow mixing chiplets from different companies?
Yes, that's crucial for building an ecosystem. Standards like the Universal Chiplet Interconnect Express, or UCIe, are being developed by a consortium of industry players to define an open, standardized die-to-die interconnect. The goal is to create a plug-and-play ecosystem for chiplets, much like we have for IP blocks today.
Okay, so advanced nodes push complexity. Chiplets help manage the cost and yield of that complexity. What helps manage the design complexity itself? You mentioned AI for EDA earlier. How exactly is artificial intelligence impacting the way chips are designed? That sounds almost like science fiction turning into reality.
It's rapidly becoming very real and is arguably one of the most significant shifts happening in the field right now. The sheer scale and complexity of modern designs are pushing traditional algorithms and human capabilities to their limits. EDA companies and design teams are increasingly turning to AI and machine learning to help.
In what ways?
Several key areas. One is PPA optimization. Designing the physical layout of a chip involves exploring an astronomically large search space of possible placements and routes. AI techniques, particularly reinforcement learning, are proving very effective at intelligently navigating this space to find layout solutions that achieve better power, performance, and area compared to traditional heuristics or human experts, and often doing it much faster. Synopsys' DSO.ai product is a well-known example here.
So AI finding better chip layouts than humans.
Or at least exploring the possibilities much more efficiently to help humans find better solutions. Another area is productivity and automation. Generative AI and large language models, LLMs, are starting to be used as co-pilots for engineers, helping with tasks like generating boilerplate RTL code, writing basic test benches, suggesting fixes for common errors, analyzing tool logs, or even generating documentation or scripts. The goal is to automate tedious tasks and let engineers focus on the more complex creative aspects of design.
And data analysis.
Yes. Data analytics. ASIC design generates petabytes of data from simulations, synthesis runs, physical design iterations, verification checks. AI-driven platforms can mine this vast amount of data to identify hidden correlations, predict potential problems like timing hotspots or manufacturing issues before they occur, and provide insights to guide design decisions. It creates this powerful interconnected feedback loop. Advanced nodes drive complexity, chiplets help manage it at the system level, and AI for EDA provides the analytical horsepower and automation to navigate the design process itself.
What a fascinating convergence. Are there any other emerging frontiers in ASIC design that we should keep an eye on?
A couple of others are worth mentioning. As quantum computing systems scale up, there's a growing need for sophisticated classical control and readout electronics, often operating at cryogenic temperatures. Designing ASICs for this interface, handling qubit control, error correction, signal processing, is a challenging but vital area.
And secure.
Hardware security is becoming increasingly critical. Instead of relying solely on software, there's a strong push to build security features directly into the silicon. This includes things like secure enclaves for protecting sensitive keys and code, physically unclonable functions, PUFs, which act like unique hardware fingerprints for authentication, and designing countermeasures against side-channel attacks that try to extract secrets by monitoring power consumption or electromagnetic emissions. Hardware is often the root of trust, so building security in from the ground up is essential in our connected world.
Okay, so we have this incredibly complex ecosystem of design methodologies, advanced process technologies, chiplets, AI assistants. Who are the key players actually driving all this? We mentioned the EDA Big Three, but who are they and what are their traditional strengths? And what about this open source revolution you mentioned? How is that ecosystem structured?
Right. The commercial EDA market is famously dominated by a triopoly, the big three companies whose tools underpin the vast majority of commercial ASIC designs worldwide.
Let's start with Synopsys.
Synopsys is a clear market leader across several key areas. They are particularly strong in front-end design, especially logic synthesis with their flagship design compiler and newer Fusion compiler products. They're also a leader in functional verification with their VCS simulator. And critically, they dominate static timing analysis sign-off with prime time, which, as we said, is universally considered the industry's golden standard for timing closure.
Okay, and Cadence Design Systems.
Cadence Design Systems also has a very broad and powerful portfolio. They are traditionally very strong in the back-end physical implementation space with their Innovis place and route system. They also have strong verification tools like their Excellium simulator. And Cadence is widely regarded as the leader in tools for custom analog and mixed signal design, which is essential for integrating real-world interfaces onto complex sockets.
And the third member of the Big Three, Siemens EDA, which used to be Mentor Graphics.
Correct. Siemens EDA, formerly Mentor Graphics. Their undisputed dominance lies in physical verification and DFM, designed for manufacturability, with their Calibre platform. Calibre is the de facto sign-off standard for DRC and LVS used by virtually every foundry and design house in the world. If your chip doesn't pass Calibre checks, it basically doesn't get made. Siemens EDA also has very strong offerings in design for test, DFT, with their Tessent product line.
So these three giants really form the backbone of the commercial ASIC design world. But then, alongside them, there's this burgeoning open source movement challenging the traditionally closed-off and expensive nature of chip design. It sounds like a real potential paradigm shift.
It absolutely is a powerful and growing force driven by the desire to lower the barriers to entry for chip design and foster more open innovation. It encompasses both EDA tools and, more recently, the hardware process information itself.
So what are some key open source EDA tools people are actually using?
On the tool side, Yosys has emerged as a very capable and widely used open source framework for RTL synthesis. For the back-end physical design flow, the Open Road project, initially funded by DARPA, is developing a complete, automated RTL to GDSII physical design suite. And tools like OpenLane provide automated, script-based flows that act as user-friendly wrappers around tools like Yosys and Open Road, making it much easier to run a complete design flow. They're open-source tools for simulation, formal verification, and other steps as well.
And the really pivotal moment for open source, as you highlighted, was the release of open process design kits, PDKs, and the associated manufacturing access.
Absolutely. That was the missing piece for a truly viable open source hardware ecosystem. The release of the Skywater technology, SKY 130mm PDK, through collaboration with Google was the watershed moment. It was the first full manufacturable open source PDK for a reasonably modern CMS process.
Making it possible to target a real factory with open tools.
Precisely. And Google's Open Silicon initiative, sponsoring those free multi-project wafer MPW shuttle runs on Skywater's process, turned that possibility into a reality for many. It means anyone, anywhere, can potentially design a chip using free, open tools, target a real manufacturing process with an open PDK, and get actual silicon back without the traditional prohibitive costs. Other open PDK efforts for different nodes are also underway.
That's incredible. What's the real impact of this open source revolution on the broader industry? Is it displacing the commercial giants?
not really displacing them, at least not yet for the most complex high-performance designs, where the commercial tools still offer significant advantages in capability, support, and foundry certification. But the impact is profound in other ways. First, democratization of design. It's making custom chip design accessible to a vastly wider audience: universities, researchers, small startups, even individual hobbyists who were previously priced out. Second, education and workforce development. It provides an invaluable hands-on platform for training the next generation of chip designers using real-world tools and flows. Third, innovation and research. The open nature fosters collaboration, allows researchers to experiment with new EDA algorithms or chip architectures, and accelerates innovation, particularly in niche or emerging areas.
So it's more about coexistence and enablement.
Exactly. For now, it's largely about coexistence. Open source is becoming a vital ecosystem for learning, research, prototyping, and maybe smaller or less performance-critical designs. Commercial tools remain the workhorses for demanding large-scale production chips where performance, power, area, and guaranteed support are paramount. But the open source movement is undeniably pushing the boundaries, fostering competition, and making the whole field more accessible and dynamic.
Okay, so even with all these incredible tools, commercial or open source and advanced methodologies, the path from RTL to GDSII tape-out is still, as you put it, fraught with technical challenges. Engineers are constantly navigating this gauntlet. What are some of the most common persistent challenges they face daily, and what are the typical strategies used to overcome them?
Right, the journey is definitely not easy, no matter how good your tools are. Engineers spend the vast majority of their time wrestling with a set of complex, deeply interrelated problems related to timing, power delivery, signal noise, manufacturability, and testability. These are the daily headaches that can delay projects or even cause failures if not managed carefully.
Let's start with that race against the clock we discussed, achieving timing closure. What makes getting the timing right so consistently difficult, especially at these advanced nodes?
Timing closure is the iterative, often arduous process of ensuring that every single signal path in the design meets its required timing constraints. Setup time and hold time across all specified operating conditions, process corners, voltage, temperature. Setup time violations mean a signal arrives too late. Hold time violations mean it changes too soon relative to the clock edge.
And why is it harder now?
At advanced nodes, the transistors themselves switch very fast, but the wires connecting them become relatively more resistive and capacitive. As a result, interconnect delay, the time it takes for a signal simply to travel across a wire, can account for 70%, 80%, or even more of the total path delay. Managing these wire delays becomes the single greatest challenge in back-end timing closure. It's a relentless battle to squeeze out every last picosecond of delay from critical paths.
So how do engineers actually fix timing violations? Is it just about making transistors bigger or wires shorter?
It's a multifaceted effort throughout the flow. Good RTL design practices, like adding pipeline stages, help break up long paths early on. Timing-driven synthesis tries to optimize the logic specifically for timing, but most of the heavy lifting happens during physical design. This includes timing-driven placement, putting critical cells closer together, automated buffer insertion, adding repeater cells to boost signals along long wires, careful wire sizing and spacing, and using faster but larger standard cell variants. And as we mentioned in the final stages, engineers often resort to manual or automated engineering change orders, ECOs, to make targeted surgical changes to fix the last few stubborn violations.
Okay, timing is one beast. Then there's the power problem. Managing power integrity. You've got billions of transistors switching potentially billions of times per second. Delivering clean, stable power to all of them must be a monumental challenge.
It's a fundamental physics problem and a major design headache. You need to deliver a stable, constant supply voltage, VDD, and a solid ground reference, VSS, to every single transistor on the chip. A poorly designed power distribution network, PDN, can lead to two major problems. First, IR drop. The resistance of the power grid wires causes the voltage to drop as current flows through it. If the voltage drops too much at a particular cell, it can slow down significantly or even fail functionally.
And the second problem?
Electromigration, EM. This is a long-term reliability issue. If the current density in a metal wire, power or signal, is too high for too long, the flow of electrons can physically displace the metal atoms, causing voids or hillocks that eventually lead to wire breaks or shorts. It's like erosion inside the wires, an invisible killer that can cause the chip to fail months or years after it's deployed.
So how do designers ensure power integrity and prevent these issues? How do they keep those billions of transistors properly fed and reliable?
It starts right back at floor planning with the design of a robust power distribution network. PDN. This usually involves creating a thick, multi-layered mesh of interconnected power and ground straps, acting like a low-resistance superhighway for delivering current across the chip. Careful analysis is done to ensure the PDN can handle the peak current demands without excessive IR drop. Strategic placement of on-chip decoupling capacitors, DCAPs, tiny capacitors placed near switching logic, is also crucial. They act as local charge reservoirs to supply instantaneous current demands and smooth out voltage fluctuations. And specialized power analysis tools are used extensively to simulate current flows, identify IR drop hotspots, and flag potential EM violations long before tape-out.
Makes sense. What about noise? The noise problem. Ensuring signal integrity, SI. I've heard that at these incredibly small geometries, wires start interfering with each other electrically, like crosstalk on old phone lines.
Exactly. As wires get packed closer and closer together in deep submicron processes, they act like coupled antennas. The switching activity on one wire can induce unwanted voltage noise onto adjacent quiet wires. This phenomenon is called crosstalk.
What problems can crosstalk cause?
It can manifest in two main ways. It can cause a voltage glitch or spike on the victim wire, which might be large enough to be misinterpreted as a valid logic transition, leading to a functional failure. Or, even if it doesn't cause a functional error, the crosstalk noise can affect the timing of the signal on the victim wire, either speeding it up or slowing it down, potentially causing setup or hold time violations. It's like trying to have a quiet conversation in a really crowded, noisy room. Interference makes communication unreliable.
So how do you combat crosstalk? Build thicker walls between the wires?
Metaphorically, yes. Solutions involve intelligent routing algorithms that are SI aware. They try to increase the spacing between potentially interfering nets, especially fast-switching aggressive nets and sensitive victim nets. Sometimes shielding is used, where quiet ground wires are deliberately routed parallel to a critical signal wire to absorb noise. Careful buffer insertion can also help restore signal integrity. And, of course, specialized SI analysis tools are used to identify and quantify potential crosstalk problems so they can be fixed during layout.
Okay, timing, power, noise. What about just making sure the darn thing can actually be built? The manufacturing hurdle, physical verification and closure, getting that final DRC and LVS clean report.
This is the ultimate gatekeeper before manufacturing. The final layout must be 100% compliant with the foundry's incredibly complex design rule manual, which can contain literally thousands of intricate geometric and electrical rules specific to that process node. Achieving a clean DRC, design rule check, and LVS, layout versus schematic report, with zero errors is mandatory.
How do teams manage thousands of rules?
It's tackled through a combination of strategies. EDA tools have built-in rule checking that runs incrementally during layout. Verification is often done hierarchically, checking smaller blocks first before integrating them. Advanced debugging environments help engineers quickly pinpoint and fix violations reported by tools like Caliber. And often, there's close collaboration and communication with the Foundry's support team to clarify interpretations of complex rules or get waivers for minor non-critical violations if absolutely necessary. It's a meticulous, zero-tolerance process.
And finally, tying back to an earlier point, the testability imperative, implementing robust DFT, ensuring you can actually test the manufactured chips for defects.
Right. As we discussed, a functionally perfect chip design is completely worthless if you can't effectively and economically test the manufactured parts for physical defects introduced during fabrication. The challenge here is to integrate all the necessary DFT logic, the scan chains, the BSS to controllers, the JTAG ports, without negatively impacting the chip's PPA. DFT logic adds area and can affect timing, and then generating test patterns using ATPG that achieve very high fault coverage, ideally detecting well over 99% of potential manufacturing defects.
How is this managed in the flow?
It requires a structured DFT methodology right from the start. Synthesis tools need to be DFT aware to insert scan logic correctly. Special DFT rule checking tools verify the integrity of the scan chains and other test structures. And advanced ATPG and test compression techniques are used to generate efficient test patterns and minimize the enormous amount of test data that needs to be applied by the production tester, which directly impacts test time and cost. It's a critical discipline in its own right.
Wow. Timing, power, noise, manufacturability, testability. It's clear that ASIC design is an incredibly complex field, constantly pushing boundaries. For listeners who followed us this far and want to dive even deeper, maybe build their own knowledge library, what resources would you recommend?
Absolutely. The field is vast and constantly evolving. but there are some foundational resources. For textbooks, the absolute classic, often considered the canonical text for digital VLSI design, is CMOS VLSI Design, a Circuits and Systems Perspective by Weston Harris. It covers everything from basic transistor physics up through system-level design.
What about understanding the EDA tools themselves better?
For a deeper look under the hood at the algorithms used in physical design tools like Place and Route, Algorithms for VLSI Physical Design Automation by Naveed Sherwani is an excellent, though more advanced reference. It gives you a real appreciation for the computational complexity involved.
And any practical guides for specific challenges?
For that critical, real-world challenge of timing closure we spent time on, The Art of Timing Closure by Khosrow Gulshan is a very practical guide filled with insights and techniques used by engineers in the trenches.
Okay, so some solid books. What about staying current with the absolute cutting edge? Where do the latest breakthroughs get presented?
For that, you really need to follow the premier academic and industry conferences. The Design Automation Conference, DAC, is generally considered the world's leading event, covering all aspects of electronic systems design and automation, including EDA tools, methodologies, embedded systems, and emerging trends.
And for the chips themselves, the big reveals.
That would be the International Solid-State Circuits Conference, ISSCC. This is often called the Olympics of chip design. It's where the major semiconductor companies and top research labs present the technical details and performance results of their latest, most advanced chip designs, the newest processors, memory chips, communication circuits. Reading the ISSCC proceedings is a great way to see where the state-of-the-art is heading.
Are there key professional organizations or important industry standards people should be aware of if they're getting into this field?
Definitely. The IEE, Institute of Electrical and Electronics Engineers, is the primary professional home, particularly through its Solid-State Circuit Society, SSCS, and the Council on Electronic Design Automation, CEDA. Industry groups like the Semiconductor Industry Association, SIA, and the Global Semiconductor Alliance, GSA, provide broader industry context and advocacy.
And standards.
Key standards that pop up everywhere include IEE 1149.1, which defines the JTAG boundary scan test architecture we mentioned. And for on-chip communication, ARM's AMBA protocols, especially AXI, Advanced Extensible Interface, are ubiquitous standards for connecting IP blocks together within an SoC. Understanding these is crucial for practical design.
And finally, for more hands-on learning, especially leveraging that open source movement we talked about, where can people go to actually try things out or get involved?
There are increasingly excellent options there. Many universities now offer VLSI design courses online through platforms like Coursera and edX. Specialized online training programs like Zero to ASIC provide very practical, project-based courses designed to take you from fundamentals to actually taping out a simple chip using open source tools.
And the open source communities themselves?
GitHub is the central hub for most open source EDA projects like OpenLane, Yosis, OpenRoad, and PDKs like the Skywater PDK. Organizations like the FOSS Foundation, free and open source silicon, actively promote open hardware development. And platforms like EFABLESS provide resources and to manage access to those Google-sponsored free MPW shuttle programs, allowing people to actually fabricate their open source designs. It's a really vibrant and welcoming ecosystem for anyone wanting to get their hands dirty with chip design.
What an incredible journey we've taken. From the basic concept of an ASIC, through its intricate design flow, the tools, the challenges, the applications, and now the future trends and resources. The whole ASIC design process is truly a testament to the power of abstraction and automation in conquering just immense complexity.
It really is. It's this highly iterative, deeply interdisciplinary process that transforms a set of functional requirements into arguably one of the most sophisticated artifacts humanity has ever created, constantly pushing the very boundaries of what's physically possible with silicon.
And at every single step, as we've seen, engineers have to strike that delicate, often difficult balance between the competing demands of power, performance, and area, the PPA triad always guided by the specific needs of the final application the chip is destined for.
Absolutely. And the evolution of this flow itself, from those early days of painstaking full custom design to today's highly automated standard cell and IP-based methodologies, that evolution has been relentlessly driven by the economic pressures of Moore's Law and only made possible by the parallel co-development of incredibly sophisticated ED tools.
And now, the field seems to be standing at another really interesting inflection point. We're seeing this convergence of the move towards heterogeneous integration with chiplets to manage complexity and cost, the infusion of artificial intelligence directly into the EDA tools themselves to boost productivity and optimization, and this vibrant open source movement that's democratizing access and fostering innovation from the ground up. These forces are really defining the next frontier of silicon development.
Navigating this modern landscape successfully requires a truly holistic understanding. You have to recognize that the logical design can't be separated from the physical implementation details, that verification and testability are afterthoughts, but parallel pillars supporting quality from day one, and that fundamentally, every single design choice represents a trade-off, often with subtle but far-reaching consequences on the final product.
So maybe the next time you pick up your smartphone or start your car or even just use a search engine online, take a moment to consider those silent, hidden engines working inside the ASICs. These custom-designed pieces of silicon, quietly, efficiently executing their specific mandates to make all that amazing technology possible. Think about the intricate dance of engineering, physics, computer science, and sheer innovation required to bring them into existence. How many layers of abstraction painstakingly built by thousands of engineers are you interacting with right now without even realizing it?